Yeah. Okay. So I'll keep. Yeah. So I would, like this to be a more interactive session. So you can, whatever queries you can just type in the chat box. Okay. So let me share my screen and then begin the session. Okay. Is my screen visible to you now? Yeah. Sorry. Yeah. Thank you for pointing that out, Srinivasa. Okay. Yeah. Once again, very good morning to all of you, and welcome to this second days of FDP on image processing and applications. Okay, so I have, you know, I do not have much knowledge of the background of the participants, so I've selected a topic, so which I believe is going to be interesting to you. Okay, so yeah, so if you look at the title, so I'm going to talk about uh, some of the works that we have done, because if you've noticed, Dr. Hemant Meena also, he mentioned that I primarily focus on surveillance and security applications, okay, specifically biometrics. Okay, in addition to that, we have done some work in some other surveillance and security related problems as well. So I'll talk about those problems also. I'll give you an overview of that. And and once I give you an overview of the research works that we have carried out in the recent past, so we'll focus then on some concepts, how we actually, what are the underlying concepts that we require to, work in these areas. Okay, so at that point, I'll actually go to the very fundamentals, basics, right? So let me know if you find it too simple or too advanced. But I'll try to keep it as simple as possible and focusing more on the fundamental concepts. So these are some of the students, my two of my PhD students who graduated in the last 3 to 4 years, and a BTech student who also contributed to a work that I'm going to present briefly in this talk. Okay, now you might see that I have not mentioned image processing or image processing. Okay, despite that being the focus of the FDP. Okay, so I have mentioned image analysis, and also I've also mentioned computer vision. Okay, now how, let's look at that first. Let's, before we actually try to understand the concepts, let's try to look at how image processing, image analysis, and image understanding, okay, which is actually what is a computer vision is nothing but is a better name, right? It's much sort of a nicer name for image understanding. So these terms, image processing, image analysis, and image understanding or computer vision, these are widely used in the literature. Okay, now you can see that you developed a system that does some image processing, or somebody might say this work involves image analysis, or someone might say that this system is a computer vision system or image understanding, that involves image understanding. Now, so there is always this confusion, right? What it means. So if you read some some standard books, for example, so authors have tried to, so of course there is some general understanding how what is called, because they all come broadly under, they all deal with images. Okay, so if you look at this, image processing involves images, image analysis will also involve images. Okay, image understanding will also involve images. So in all these cases, right, so the input is an image basically, right? So input is an image. So let's say you can think of this way, you're doing some processing. Okay, you're performing some processing. Now input is an image, and this distinction, image processing, image analysis, and image understanding, is based on the the kind of output that we are generating. Given an input, you're processing it, okay, at some level. Now, depending on what sort of output we are generating, that we are creating, you can call it a image processing system or image analysis system or a computer vision system. Okay, so that's exactly what is described here. So when I say image processing, that's a very low level process. You can define it this way if you want to sort of define it. So this is a basic understanding in the community. So when I say image processing, input is an image, output of the processing also is an image. Okay, so if you're performing some processing here, input is an image, and this is your input image, and this is your output image. There are examples. I've mentioned some examples here. So this is from your classic book on image processing, okay, by Gonzalez and Woods. Now, if you see this, uh, image, sorry, noise removal, or rather noise suppression, denoising, okay, they all mean the same, or image sharpening or image enhancement. Okay, so these are some of the tasks or some of the problems, okay, where, for example, if you're talking about denoising, input is a noisy image, output is a denoised image. Okay, noise suppressed to a great extent. Okay, similarly, if you're talking about image sharpening or image enhancement, input is an image where the features are not very clearly visible, and after processing you have enhanced the image. Okay, the edges are clearly visible. Okay, in fact, is sort of, the underlying concepts are, for example, you might be using some sort of a high pass filter here. In most cases, we use for enhancement some sort of a high pass filter that will enhance the high frequency components, like, edges, and so on, right, of the objects. Now, so if you're dealing with a problem that has input is an image, input of course is an image in all these cases, output is also an image, then we can call it image processing, which is actually the lowest level of processing that you can do with an image. Now, if you look at the second, if you go slightly higher, okay, and then comes what we refer to as mid-level processing. At the same time, remember, there is no clear-cut boundary like this here. You know, it's all understanding in the community. Okay, so that's what I'm trying to sort of clarify right at the beginning, right? Image processing, image analysis, and image understanding. How they are different, and what is typically considered image processing, what is considered image analysis, and what is image understanding on computer vision. Now, if you look at the mid-level process, so you can think of, again, it's some sort of a processing that we're performing on the input image. Okay, and to obtain here, the output is different here. Okay, so for example, here it's mentioned, yeah, input is an image, output is an image. Here input is an image, output is certain attributes or certain features that you compute from the image. Okay, so for example, for example, let's say you're performing what is called, there are some tasks mentioned here, image segmentation. Let's talk about image segmentation. Okay, if you're talking about image segmentation, what is image segmentation? For example, let's say you have an image. Let me just give you a simple image here, simple image segmentation problem. So you just have one object in the foreground. Okay, rest of it you consider as a background. Okay, so maybe a portrait photo of a person, for example, or an animal. Now, once you have this image, and if you want to perform segmentation, as the name indicates, segmentation is all about dividing or partitioning, okay, the image into multiple meaningful regions. Here, if you look at this, how many meaningful regions exist? One meaningful region, of course, all these pixels, that the set of pixels that form this foreground object here in this person, maybe this person or an animal, whatever. Okay, and rest you consider it to be background, something typically of not of our interest. So if you're performing segmentation on an image like this, output expected to be, okay, so yeah, what you're basically saying is that you're, yeah, let me just tell you, yeah, so you're basically generating a set of pixels that form a meaningful object, right? So it's sort of a, you can think of this as a binary image also, right? So where you have, you'll make all this, if it's, for example, what we refer to as semantic segmentation, every pixel is given a label. Okay, so whether it's part of this class or the other class. In this case, you're considering two classes, so you can give all of them a class 1 information, class 1 label, and rest of the pixels as class 0 label. Okay, so it's what so segmentation can be seen as some sort of a pixel level classification. Okay, because you want to uh, club them together. If you want to form a subset of all these pixels are part of the object of interest. Okay, which forms a meaningful part in this image, and rest of these pixels here, they are part of the background. Okay, so they can be given each pixel can be given a label, this common label, so that they can all be, again, you have two subsets here. Okay, so you have all the pixels here. Some of the pixels are now part of this subset, and the rest of the pixels are part of this subset. If you're considering two regions, there may be three regions also. For example, there's a let's say there's some road here, street. Now, and whereas this, rest of it is, let's say, water. Okay, rest of it is water. So you have a road here, and then you have an object. So in this case, yes, you have now mainly three meaningful regions. So you have to combine those pixels that belong to those regions. So pixels that belong to this region, you will give it one label. Pixels belonging to this region, of course, this is the part of the object of interest, you'll give a second label for this. And rest of it, let's say if this is all water in the background, so you can give all these pixels the third um, label. Okay, now that way you will be forming, now in this case you'll be forming three subsets. Okay, given a set of pixels in this image, a subset of pixels that form this region, that are part of this region, and this part of this region, and so on. So it can be more than three as well. I'm just so if you're performing such tasks, we typically refer to this as mid-level processing or image analysis. Okay, so you're analyzing the image and then trying to come up with some stuff. In this case, of course, trying to partition into meaningful regions. Okay, so based on certain attributes. Similarly, if you're performing for example, object recognition. Okay, so what is object recognition? I'll talk about that later as well briefly. So given an image, you may have you know maybe let's imagine this is of an office, indoor office scenario. Now you have, let's say you have a table, you have a computer, okay, and so on, maybe a table lamp, and so on, maybe a chair. Now, given this image of an office indoor scenario, now if you're able to recognize, okay, so for example, individually, okay, so in fact, it might involve segmentation. I'm not going to talk about how exactly this recognition is performed. So if you're able to perform that, if you're able to identify that this is a computer, this is a table, this is the chair, uh, table lamp, and so on. So how do we do that? Yes, you would actually use some features or attributes of this object and then perform recognition. Okay, so slightly the next level. Now, once you are able to do that, yes, given image has these these objects. So that basically some sort of an attribute information about the given image, and that is why that all that is part of your image analysis. Now, then you might wonder what is computer vision or the next level of processing. If you look at this level of processing, you can go further. Okay, you can go further, uh, where again, in fact, here we are talking about input as an attribute, but where do we get the attribute? We get the attribute from the previous step. And in order to get the attribute, it's also interesting, in order to get the attribute, you may have to perform, in most cases, some sort of noise removal, sharpening, and so on. So if you are working at this level, it's assumed that yes, you do perform this as well as you do perform this. You cannot directly perform this. You cannot directly get attributes here. Okay, so let's not get confused with that. So yeah, so essentially input to the even the high level processing is actually an image. Okay, so which is more likely in most scenarios will undergo low level processing and some mid level processing, and those outputs are fed into the. So overall, yes, if you're talking about computer vision system, it will involve some low level processing, it will involve some mid level processing, finally to get high level understanding. Okay, so here input is just attribute, but attribute actually comes from attributes. They come from this stage, and in order to get attributes, you may have to improve the image, enhance the image, suppress the noise, and so on. Okay, so the very fundamental thing: image processing, image analysis, and finally computer vision. So if you're talking about, for example, scene understanding, as I said, based on, for example, you have an image of a office space, indoor office, so you have table and other things. Now at this point you are able to recognize the individual objects, okay, with the help of image analysis. Now given that information, yes, the scene has the computer, desktop computer, there's a table, chair, lamp, and so on. Now if the system is able to sort of um, providing information about, understand the scene, basically, for example, if you're talking about this particular problem is understanding the scene, given these set of objects, given that the scene has these set of objects, recognized objects. See, if the system is able to sort of providing information, okay, make sense of what that means, right, what sort of scene it is. So if it's able to tell you that yes, this is a scene, this is an image of an indoor office space, yes, that's what we call scene understanding. Similarly, you can think of some other, for example, let's say image of a beach, right? You have a lot of waters and then maybe a lot of sand here and some few trees and a few people and so on. Now given this, so initially you may perform noise suppression, noise denoising, image sharpening, and then followed by recognizing or segmenting these regions. And based on that information that you have, if the final at the final level, highest level that you perform, if you're able to identify that yes, this is an image of a of a beach, and then you have there's a lot of there are few people, there are few trees, and then sand and a lot of water. So that understanding, if your system does that, okay, then we say this is computer vision system, right? Because we are trying to understand the scene there. So similarly, autonomous navigation, something that we recently worked on, okay. So we developed a completely uh, you know autonomous navigation system completely based on RGB images, video rather, okay, frames. Now that was meant for you know visually handicapped, visually challenged people. Now, so some sort of a device so a person can wear. Now with, of course, we have taken the advantage of the advancements in for example, deep learning, specifically large language models and vision language models and so on. So images captured continuously with the help of a camera, that is some sort of a wearable device, that we have developed a prototype of it. Now this captures images of the scene, and then we process that, onboard processing, okay, using some single board GPU based processing. Now once it's processed, this gives the user a feedback, sort of more like an interaction, not just a feedback. So user can provide the query, speech query, and then it can provide. So for example, user can ask, do you, what user can ask the system, okay, what are the objects in front of me, okay. So you can provide, analyze the image and then provide using, as I mentioned, large language models and so on. So you can provide information to him. So you can further ask, for example, can you take me to this particular object, okay, let's say bag that you can see. Now yes, in that case we have to perform what is called, we have to find the path, optimal path to the object, and then provide this information to the user. So that's some sort of an autonomous navigation, okay. So yes, so that involves not just finding attributes and then using those attributes, making some sense of the entire scene, okay. So that's computer vision highest. So yes, so most of my work is broadly falls into this category, but that doesn't mean we don't use image processing at all. So all that we'll use at the very beginning, when you capture the images, a lot of times we perform some very fundamental image processing tasks. Now, just give you an overview of the work that we have done in recent past. So, focused on crowd counting, again, is a surveillance and security application, specifically on weakly supervised approaches. Okay, so I believe in machine learning, so you're familiar with supervised learning and unsupervised learning, and then there are, of course, some other semi supervised, weakly supervised, and so on, right? So this particular work was on weakly supervised methods, developing weakly supervised methods for crowd counting. So crowd counting, if you're not aware, the crowd counting problem is given an image. I have some results also, I'll quickly show those. uh, those results, qualitative results. Let's say you have an image, and there's image of a crowd, a lot of people gathered, so indoors or in an outdoor scenario. Now, the problem of crowd counting is just to estimate the number of people in the image, okay, static image. Now, yeah, how is this going to be useful? Yes, of course, crowd is just part of, actually, crowd counting is very much part of crowd management, okay, which is of course a much more broader, or major topic, where there are several other things involved, behavior of the crowd and so on. But in addition to that, crowd counting is actually provides macro level information to crowd management. So it actually forms a very important component of the crowd management, estimating the number of people in a specific, you know, given this visual field. Okay, so an area, basically an area, and we specifically focused on active learning and uncertainty quantification. Now, what do you mean by active learning? In active learning, what the difference here is, in a typical learning, what we do, you have a model, right? You're developing a machine learning model or a deep learning model. So you provide a lot of data and it learns. But in active learning, given this data, the model selects some informative examples from the, or data points from the data set, and only uses those more important ones to learn. So it's like, instead of you providing all whatever exists to train the model, so model itself picks up some informative examples and then learns from it. So basically the idea here is you can reduce the number of uh, examples required to train a model. Okay, we can still get, despite that, for example, even with 50%, I'll show you the results that we obtained. Even with 50% of the entire data set, so we can achieve the performance which is as close to 100%, very close to 100% of the data set, right? So now the advantage, of course, is this is more advantageous when it comes to, uh, we know that in supervised learning we require the process of labeling, right? Some annotation or labeling needs to be performed, and in most cases we require some expert, right? For example, if you have a medical image, if you're working with a medical image diagnosis problem, so let's say it's an image of, let's say an image of MRI image of a brain, right? There's a tumor, for example. Now, in this case, if you want to train a model that performs tumor detection, okay, so then you need to first provide a lot of supervised images. When say you have an image, also you have a doctor annotating or labeling this region as a tumor, okay, whereas rest of the region is absolutely fine. Now, you need expertise, right? Of course, labeling is a manual process. Most cases require expert effort as well. So therefore, it's time consuming and as well as expensive, right? So with active learning, we can reduce this number of the labeling required. The number of samples with labels can be reduced significantly, and achieve the performance which is very close to using the entire data set, right? So that's an advantage of active learning. Now, uncertainty quantification again is an area where we're talking about. So see, often models just give you prediction. Okay, it does not indicate how confident is a model in this prediction. Okay, so often, in fact, you may have seen, right? For example, when you're asked to evaluate something, right? A lot of times, for example, when I review papers, okay, if you review if you when a paper comes to me for a review, research paper comes to me for a review, often one of the questions is, how confident are you in evaluating this work, right? Because it's possible that this paper or this work may not fall exactly in my area of expertise. So so the person wants to see my comments on the paper. Along with it, he wants to see how confident I am. Okay, so how confident I am in this work, how much do I understand this area. Basically, that's what it is. So you give a score, maybe on a scale of 0 to 5 or 0 to 10, that I'm very confident, I'm not so confident, and so on. Okay, similarly, so here what we're trying to do is uncertainty configuration. So in addition to the prediction that the model makes, can the model also indicate how confident the model is in its prediction? If it's very confident, then as we should be, we can take it as it is. Okay, but if it gives a prediction along with a very low confidence score, that means this may be wrong as well. Okay, so that's basically what uncertainty quantification is. So we have done that for crowd counting. We have incorporated that concept of uncertainty quantification in crowd counting problems. So, and then of course, biometrics, something that I've been working for several years now, maybe 15 or 20 years now. So here specifically in the recent work, we focused on high resolution fingerprint recognition. Okay, so in high resolution fingerprint recognition, if time permits, we'll talk about these. But uh, once I give an overview of this, so I'll focus more on the big fundamental concepts. Okay, so and if there's time at the end, I'll actually focus on this particular problem and introduce to you what, for example, we'll talk about how high resolution fingerprint is different from the standard resolution fingerprint. Right, standard resolution fingerprint that are often used for often used in law enforcement and so on. These are 500 dpi images, 500 dots per inch. Okay, dots per inch or pixels per inch rather. Okay, dots per inch, it actually comes from the legacy printing domain, where if you have more number of dots per inch, your resolution of the print would be better. But here we are talking about digital images, so it should be pixels per inch. But still we use the name this dots per inch. So 500 dots per inch or 500 pixels per inch is what we consider as standard resolution fingerprint. Suffices for most applications because we can capture some useful information from those fingerprint images, and to do what, to recognize the person. Okay, to recognize who this belongs to. So I'll talk about a little bit of this later. And then what is high resolution? So if it is around or even greater than 1000 dpi, there is no standard definition. So some standards might have recently defined this. Okay. Now, uh, if the advantage with higher resolution is you can see some additional finer details. Okay. You can Yes, of course. Yeah, I'll provide that. We have published some papers in this area, so I'll actually provide. I do have on my slides references to those works. Okay, and the first high resolution fingerprint recognition was actually explored by. This was explored by Professor A.K. Jain. Okay, so Professor A.K. Jain is one of I would say pioneers in this area in fingerprint recognition, considered sort of father of fingerprint recognition. So he is the one. His research group in 2006 explored for the first time explored high resolution fingerprint. Can we achieve additional details from high resolution fingerprints so that we can improve the performance of recognition? Okay, see, basically we do the same thing, right? Whether it's a standard resolution fingerprint or high resolution fingerprint, we are trying to identify, given a fingerprint, we are trying to identify who this belongs to. Okay, so it's just like face recognition, right? Which is something more relatable to us. Given an image of a face, we are trying to determine who's who is this person. Okay, or yeah, who does it belong to, rather who is this person, right? Similarly, given this fingerprint, we're trying to determine who it belongs to. So that's what recognition is about. Biometric recognition is all about. Okay, so in high resolution we can see some more details as compared to standard resolution, and those finer details will help us improve the recognition accuracy, or in general performance. Now, when it comes to fingerprint recognition, specifically, there's something called identification. In identification, indexing is very important. What is identification? Identification happens in a very typically in a in a forensic scenario where you have just a fingerprint. You just have a fingerprint, and we are trying to identify who this belongs to. Now, what we typically have, like for example, forensic agencies and for example FBI, you can read about it. They have a database of millions of fingerprints or billions of fingerprints. Now there are several fingerprints in their database, each with an, of course, there's some user information, okay, associated user information. Now if you have to identify who this belongs to, then we call it 1 to n matching, 1 to n comparison. Okay, why is 1 to n matching? Because you just have one image, you're trying to decide who this belongs to. Or if it's a face image, yes, you have a face image, and you're trying to determine who this person is based on a database of images. For example, you have a face image of a person X, another face image of a person Y. So a lot of face images in the database, and this can be considered what we call a query. It's very similar to, search, right? The search framework. In search, what we do, typically it's a text-based search. Of course, this is image-based search, right? You provide in Google, for example, you type in your query, and then of course, on the internet, there are many sources where there is some relevant information. So what are we trying to retrieve? Based on this query, the Google returns or retrieves the most important, for example, sources where there are information relevant to this query. That's exactly what we're doing here. Now here what we do is we give an image. So we want to identify uh, those face images that are most similar. So identification, what we do is we expect the system to come up with what we call top K matches. Okay? Top K matches. Now what that means, given a fingerprint or a face image, we want to identify those images, those for every image there's an identity saying that this is of this user. So if you're given this image, if you're able to see that yes, this is the most similar image in the database, and the person name is X, and that this is a second most face image in the database, and the name of the person is Y, and so now once this is done, once this is available to you, so typically this is how identification system works, and then we can actually manually look at it. Okay, so we can, let's say top 5 is retrieved by the system, so we can actually manually look at it and say that yes, it appears to be this person or this person. So we don't typically rely only on the top match. The reason is, top if you just rely only on the top match, your performance may not be very good, accuracy, right? But instead what you're trying to do is you're trying to generate a sort of a short list using the algorithm, using the method, and then based on, once you have this shortlisted candidates here, so you can just look at it, and then maybe this may be the right, it's always possible that the person, this is what we call rank 3, this is the rank 1, rank 2, rank 3, rank 4, rank 5. So this may be the actual person. Okay, but it's possible that algorithm finds the first two are wrong. Okay, but it still is, in terms of facial features, they are very similar, at least as per the algorithm. So that is what identification is. And identification is a computationally very challenging task, very intensive task, because it involves 1 to n matching, and n can be very large number. Okay, so as I mentioned, some of these law enforcement agencies can have database that has millions of identities. Now in order to speed it up, we perform what is called indexing. Okay, uh, so what is indexing, details of it we will not get into that, so that's going to be all biometrics then. So, and of course, feature extraction is a very important stage in a biometric system. I'll talk about that. Okay, so this is a very important stage, some of you may be already familiar with, because this is something pipeline you typically see that, right? So I mentioned that earlier as well, for example, attributes, right? So in general, this is what it means, features. Now finally, once you have, it's like this, given an image, what we typically do is, let's say face image, we compute certain features. Okay, so it can be, for example, maybe width of this eye, width of this eye, length of the nose, and distance from this eye center to this eye center. Those are what I call features. Okay, given this image. Now based on these features, so we form a numerical feature vector, and based on that, so if you have to compare, so in a simple, in order to simplify this, let me tell you this. If you have to compare two face images to see how similar or how dissimilar they are, so you compute those features, form a feature vector, numerical feature vector. Similarly, given the other image, you compute the same set of features from this image, and then make a comparison of these two vectors. Okay, so one of the easiest thing to do is, given two vectors, how do you compare? You can use what is called Euclidean distance, for example. There are, of course, other distance and similarity measures, but Euclidean distance is one of the simplest ways to actually compare two numerical feature vectors, right? So if the Euclidean distance is a very small number, it's a scalar value. If it's a small number, this indicates that these two images are very similar. Okay, so it's possible that it belongs to the same person. These are two images of the same person. However, if this value is very large, that indicates that the distance is a distance measure, so it indicates that they are very different. These features are very different, therefore this is expected to be of two different individuals. That's a comparison I'm talking about. Okay, now Yeah, so in fact, in a recent work, we've also tried so incorporating this face recognition capability, providing drones with that capability. The advantage of that is, with advancements in drone technology now, for example, if you have a large crowd here, okay, so at a particular location, large crowd, and let's say a law enforcement agencies in India, for example, police is looking for a particular person. They have information that yes, the person that they are looking for, they have an image of him, for example, and or a sketch. Now the person they are looking for is in the crowd. They have some information. Now how do we uh, find the person? Yes, of course they can send people into the crowd and looking for this person. That's of course not an efficient way. But with advancements in drone, what we can do is you can just fly a drone over the crowd. Okay, hardly takes a few minutes. Drone comes, of course the drone has a camera mounted, and then we have a video of the entire crowd. Okay, assuming that this entire crowd is captured, so we have a video, and where there are several face images. Okay, so several people. So now that we have this as a query and this as a database, match these to all. Okay, so this can be done real time as well. We have done that real time. I'll show you the results quickly. So once you do that, maybe if this matches to this person, so yes, which means the person we are looking for is in the crowd and he's in this particular location. Okay, so if it can be done in a real time, if it's not real time, yes, it's possible that this person has moved away as well. Yeah, so this is something that basically providing drones with this face recognition capability. And we've also extended this work, crowd counting work here, where we relied mainly on visible images. The images, as you would know, an image can be, I believe you're familiar with that, right? When you capture image acquisition, right? There are different kinds of image acquisition devices. Okay, typically we work if you look at the electromagnetic spectrum, right? So we have X-rays, gamma rays, and so on. So if you look at in terms of the wavelength, right? So increasing wavelength. Now we have what is called visible spectrum here, from around 400 to 700 nanometer. Okay, so this is the wavelength at scale I'm talking about, from lowest to highest. Now this is what we call visible spectrum of the electromagnetic spectrum, visible region. Now the general purpose camera, yes, we operate in this region, right? We have the visible light that falls on an object. That's basic acquisition, the underlying principle. So you have some sort of light falling, okay, visible light falling, and then the reflected light is captured by the sensor to create this digital image. But yes, we already aware, other regions can also be used in imaging, or X-ray imaging, for example, is very popular. Although it's not based on reflection, based on absorption. But you have, for example, X-ray source tube at one end. So you have let's say a part of a body that you're imaging, and then you have the detector at the other end, right? Based on the absorption profile, and that creates a contrast, and then you create an image. Similarly, there are other, for example, infrared region. Right after this, we have what is called infrared region. Okay, and there also you have near infrared, far infrared. Near infrared, in fact, is used in the night vision cameras. Okay, to create image of completely dark scenes. And then you have far infrared regions, or thermal images, which is actually a passive imaging. You don't require an active source of energy. Rather, uh, the object that we're trying to image, assuming that it has some temperature difference with the rest of the objects. Okay, so if it's some temperature or some warmth, so it emits radiation in that far infrared region, and that can be detected by the appropriate sensor to create an image, contrast image. So we extend that and work basically to combine multi-model, combine visible as well as infrared, so that this system can work even during the night. Okay, so it's sort of an adaptive selection. Okay, so if this quality of this based on the quality, right? This fusion is not a very straightforward fusion. We've done that based on the quality. So if this is good, so the crowd counting will entirely depend on this. This is good, if the quality of this image is good, will depend on IR images. Or if both are required, we combine them together to estimate the number of people in the crowd. Yeah, I'm not going to getting into the details of this models, because this is for sort of more advanced. So then we'll have to cover entire deep learning and see how transformer architectures, transformers work, and so on. So we have a transformer backbone here. Based on that, we've built this entire system that, given this image of a scene, okay, so basically it performs patch-wise estimation, and then you see it actually predicts, directly predicts. There is no detection involved here. We're not trying to detect where people are. We're just given an image, we are trying to come up with a prediction. So it's a regression problem. We're predicting the number of people involved. Okay. Yeah. For example, some of the results here. So let me just present you. You can see here. This is an image of an uh, some sort of a seminar hall, and then you can see here a lot of people inside. And camera, of course, is a static, which is point captures the image, and the ground truth, which means the actual number of people in the scene. Okay. So how is this determined? You would know, right? In machine learning, if you have performed supervised learning, you require ground truth. Okay, the label, or the target value, actual value, all mean the same. Now here I mentioned earlier, so that's typically done manually, right, by counting the number of people by a human, right? So, and whereas the estimated count, we've trained the model, and then we estimated this on this data, this image, and the estimated count was 86, right? Total number of people here. Similarly, some more challenging work here. If you see challenging scenario where there is a lot of light variation, illumination variation here. Some parts of the image is well lit, whereas some regions are very dark. Okay, and again, there's another issue here, the scale variation, right? Some of the objects are that, of course, is a problem with all cameras that are you know fixed at a location. Okay, so if it's not moving, so you'll have always have because some of the objects are very far from the camera, and so they will occupy only a small region, whereas this object is much easier to count this accurately. Now the same here as well. So scale variation as well as illumination variation, they pose significant challenges in estimating the crowd count. And in this case, the estimated count was 168, whereas the actual count was 161. Now, again, this is actually a pole mounted outdoor scenario, okay, where you have a pole mounted camera, just like a street light. So again, crowd is gathered. So you can see here significant scale variations, okay, and and some other objects as well. That's again, might resemble like people, and then all that results in leading to inaccurate prediction. Okay, so again, this is further highly challenging problem. Again, this is a camera captured camera which is fixed at one point, so which captures this crowd gathered here, maybe some sort of a protest or something. Then you see here the issue is the scale, right? It's a very the distance from the camera to the objects of interest here, which here is of course number of people. The people here is very far, and that results in that poses significant challenges in counting accurately. And then, as I mentioned earlier, we've done active learning. We looked at how active learning concept can be incorporated for crowd counting, so that labeling can be. You can imagine, for example, if you have to label this image, it takes a lot of effort. Okay, although labeling for crowd counting will not require experts, right? Anybody can label, anybody can count and provide this ground truth count. However, it's a major challenge. Okay, time consuming. So in general, it's expensive as well. So how do we reduce that? In order to address that problem, we looked at active learning, where the model during the training stage will actually pick up more informative images, and those will have to be annotated. So we don't require annotation of the entire data set, but we do that in batches. Okay, for example, I'll just present the result here. You see, what we've done is I'll skip these. So if you look at the last row here, with 50%, we have selected these samples based on uncertainty. Let's not get into those concepts. We just used 50% of the entire data set. So we require only labeling of those 50% of the data set. And with that, if you see, we have performed this on 4 different data sets. Okay, these are publicly available data sets for crowd counting. And the performance is, in terms of, these are mean and mean square error. it's a regression problem basically, right? You're estimating the count and there's an actual count. So you can just use MAE and MSE to evaluate performance evaluation. Now, if you see this, even if you compare with 100% data, if you use 100% data, this is what is achievable, 59. However, with 50% of the data selected actively by the model, we are able to achieve 65%. Okay, it's of course it's poor, but then relatively we are just using 50% of the data. But here you see with 100% you are able to achieve 99, with 50% we are able to achieve 105. Okay, similarly, they're all, you know, in some cases it's very close. For example, here, okay, on this it's a very challenging data set compared to these data sets. This is a very challenging data set, and look at the performance here. With 100% we are one is able to achieve 61.5. With only 50% we were able to achieve 61.5 error. Okay, so again this is an error, and this is slightly less than this, but then uh, we are using 50% more data. Now, yeah, so this is, as I think I mentioned this to you earlier as well. So yeah, that was a biometric thing. We also extended crowd counting using AI. Okay, so sorry, we've actually using drones. The advantage with that is, so far, if you look at all the previous works, here crowd counting involved processing images captured by camera which is fixed at a certain location. In most cases it was pole mounted cameras, okay, or ceiling. In some cases, in indoor scenarios, this may be from a ceiling and or a wall and so on. Now here, what we sort of envisaged was, so this was done for the first time. So we have a drone with a camera mounted here which actually flies and then again captures a video and then comes back with the video, or you can perform this real time. Okay, and then we analyze the video and then count the number of people in the video. So this is more advantageous. If, for example, if crowd is gathering outdoors and law enforcement agencies want to have an estimate of how many people have gathered, so counting them using fixed cameras, you will have to pre-install, you'll have to install cameras, maybe multiple cameras covering this entire region and so on, right? So that's not something very efficient way of doing it. But with the drones available, you can mount a camera and then fly the drone, make sure that you cover the entire region, and then come back, analyze the video to estimate the number of people. How exactly we've done it? So we've not published this work yet. So at this point, yeah. So this is a result of the thing that I mentioned. If you look at this, of course, this was done institute and our own department students. Now, if you see, this is a small crowd, of course. Now, you see, we have a query. Let's say, imagine law enforcement agency is actually looking for a person. So they have a query. They know they're looking for this person. They want to know whether he's in this group, in this crowd. Okay. So again, this is a small crowd. So, but this was just a lab level demonstration. Now, we are flying a drone, and we are in real time. We are trying to identify. Yeah. So the person they are looking for is Iman. Okay, so this person. So this is provided as a query, and we have the video that the drone captures, which has multiple face images for all these people, around 8 to 10 people. And this matching is performed in real time to identify, yes, Iman is present, and that is what is indicated here. Okay, this is a person. And we've, yes, in fact, there are challenges. So you might wonder, how will a, you see, in fact, in this case, it also happened that students were not informed. So they were actually looking at the camera, looking up at the drone. So that's also something helped improve the accuracy, but that's not expected, right? So if the object is not cooperative, okay, so he knows that, yes, there's a drone flying, it may be looking for him, so you might try, may not look at it. So can we do that with partial, or what happens if the drone is flown at a higher level and so on? Does that affect the accuracy? We've done some studies as well. So yes, if you increase the height of the drone, so because the angle changes now, right? Typically in a face recognition system, we would like to have what is called a perfect frontal shot. This is the most this is the easiest one to handle, right? If you have a perfect, like a, a mug shot, okay, that we capture for passport size, passport application or passport size photo basically, right? So you look at the camera, and then you have what is called a mug shot or a frontal shot. Now, if you have these sort of images, face recognition becomes a very trivial task. But then challenges are like pose variation, the perspective variation. The camera looks at the person from a very different angle. So look at it. So yeah, so you can see here, we're now flying the drone at much higher. Again, since some users, of course, did look at that, but others, you can see here, and more intelligent, smart students, they did not look at the drone. Okay, so and that actually should have been the case. Okay, so the people should not actually look at this camera and just look at the camera in the drone, and so that so that actually helped us improve the performance here. Now, yeah, let me come back to, yeah, let me now focus on the concepts. Yeah, let me know if you have any questions so far. Okay, so is everything clear? Okay, great. Okay, so now let's say, let's try to understand, let's slightly go back, try to understand what are the fundamental concepts that we need to know if you have to develop these systems. Okay, some of those things that I mentioned, for example, face recognition system, fingerprint recognition system, or drones with face recognition capability. What are the fundamental concepts that we require? Again, I'm not sure if you're familiar with this. So we require what is called the concepts of pattern recognition. Okay, so you see, actually, this computer vision, biometrics, pattern recognition, they're all, you can draw circles like this, they're all overlapping. Okay, they cannot be just standalone, right? So this biometrics, for example, computer vision here, which of course, we know what it is. So it's also related to image processing and image analysis, and which is actually the focus of this workshop or FDP. Now here we have what is called PR. Although we consider them as different domains, but they're all overlapping. Okay, so if you want to work in one, for example, in this area, you need to know PR, fundamentals of pattern recognition. Also, you need to know computer vision techniques, right? Why? I'll try to explain that, how they are, overlapping and how they are related. Now, if you look at this, where does this come from? Pattern recognition. Okay, let's look at this, for example, recognition. The term recognition is often used. In fact, biometric recognition, right? Although in short, we just call biometrics, but it is actually biometric recognition. Okay, recognizing the people, identifying is a specific term. I mentioned to you that given an image and given a set of images in the database, identifying who this person is, this is a specific task in biometrics. This is a specific task. There's something called verification also, if you are interested. The second task in biometrics is verification. What is verification? In verification, what we do is we provide, for example, our fingerprint. So in fact, in Aadhaar, we do verification. I think all of you are familiar with that. What we do, we provide our fingerprint. Okay, for example, at the time of updating our data and so on, we provide our fingerprint, and along with it, we provide our Aadhaar number, some unique identifier. In this case, how the matching works is, again, you have a database of large number of users, identities. So with every fingerprint image, we'll have that additional information about his name or Aadhaar number and so on. Now, in this case, what happens is we do not perform what is called one-to-n matching. In identification, we have to perform one-to-n matching because we just have a biometric data. We do not have anything else to provide as an input to the system, and we have this database is same, okay, or similar in both cases, whether you perform identification or whether you're performing verification, database is same, but the input that we provide is different. Here we just provide a biometric data, here we provide, along with biometric data, you provide an identifier. That makes it much easier. So given this information, you're basically seeing that I am this person. Okay, it's a basically claim. Now the system has to verify whether the claim is correct, whether the fingerprint that you gave and the other that you provided is of the same person. How to verify? Very simple. So given this Aadhaar number, let's say this is the number, okay, retrieve this fingerprint image, okay, only this, based on the information that you provide, or if you have given the name, that's fine. Then based on the name that you provided here, retrieve that user's fingerprint image and then match with this. If there is high similarity, again, typically there's a system here, so we'll have a system threshold and so on. So if the similarity score that you compute is greater than certain threshold, you can say that yes, user is verified that this Aadhaar number and the corresponding fingerprint that we have on their database, that matches with the fingerprint that has been provided right now for verification. It's possible, for something called imposter, we call it imposter. Somebody knows your Aadhaar number, so he, maybe for whatever reason, he's providing he provides his biometric data. Okay, of course we can provide fake biometric data also, we are not talking about that. Okay, there is, again, so there's that opens up completely different research domain of presentation attacks in biometric systems and so on. But here you can think of this way: person provides his own biometric data, fingerprint, along with it, however, he provides maybe your Aadhaar number. Okay, he knows your Aadhaar number, he provides that for whatever reason, some misuse here, okay, some malicious intent. Now, system ideally, then what we do, so once this is given as an input, system will be only able to retrieve that corresponding user's fingerprint, and this ideally should not match. And that is where verification should fail, because this user, the person actually has provided wrong Aadhaar number. He's saying that I am this person. In reality, he is not. Okay, so that should be established by the system, because when you retrieve his corresponding biometric data and match it with what he provided right now for verification, that should not match. There should not be similarity, or should not be, the similarity should not be greater than certain threshold that the system, the threshold that you have set. Now, if that happens, we say verification has failed. Sometimes our own fingerprint verification fails. That's a different thing, right? Maybe there are a lot of issues here, cuts and bruises and so on. Typically, it happens with people, labor class people who actually do a lot of tasks with their bare hands. So their fingerprint will have a lot of cuts and bruises, and then it may not match with the fingerprint that they had provided during enrollment. All this data that are part of the database are during the enrollment. Okay, of course, in database also gets updated. Okay, and that's what we do. For example, for kids about greater than 5 years, it's mandatory that they should update the fingerprint. The reason is, as we initially, in fact, in the childhood, the patterns might slightly change. Okay, with age slightly change, but after beyond an age, it remains very stable. So stability is something, permanence rather. The permanence of this fingerprint features is also very important. Some of the patterns are, for example, face. Face is something that is more prone to changes with aging. Okay, so of course, that's also a research area. People have actually looked at how we can develop face recognition systems that are less sensitive to aging. Okay, aging invariant face recognition, elimination invariant face recognition, post invariant face recognition. These are some specific topics in uh, face recognition or in general biometrics. Now here I'm talking about pattern recognition, the field of pattern recognition. What is it? We're trying to understand how is it relevant to us? Why do we require some fundamental knowledge of pattern recognition? The reason is, so let's look at where exactly this comes from. If you talk about recognition, so why is it called recognition? First of all, what is recognition? So let's talk about ourselves. Okay, so let's talk about human beings. We perform, for example, pattern, forget about it, we perform recognition, several recognition tasks, not just one or two. We perform several recognition tasks, and all that we do it with a lot of ease or effortlessly. Okay, we do this with effortlessly. So what am I talking about? For example, do we do face recognition? Do we perform face recognition? I'm talking about human beings. I'm not talking about systems that perform face recognition. Do we perform face recognition? Yes, the answer is yes. And in fact, this is a primary way we recognize each other, fellow human beings, right? For example, let's say you go to office uh, and then you see your colleague or your friend. So immediately recognize him. How? So what I'm trying to say is we perform face recognition. So this is a primary way using which we identify fellow human beings. Okay. Yes, if, for example, if this person is very far away from you, you cannot see him, then we might use some other features. For example, gait, the style of walking. We do use that as well. For example, you are here and your friend may be walking maybe a few hundred meters away from you, but you can still see him. Okay, still see him, but you can't see the face clearly. But however, from the style of walking, the way, the manner in which he walks, something, there is a pattern there, right? Based on that pattern, that of course, you have learned basically. Okay, so you have all that information in your brain. So you look at that, and then you get an idea. Yes, it appears to be my friend, this person. So that's what we call, in biometrics also we do use that. So if, for example, so forensic scenario, we use a lot of gait information in forensic scenario. Let's say the crime happens, and then we have, surveillance cameras have not captured clear face images, for example. But let's say there's a camera here, there was a camera here, and the person, the suspect, he walked very far away from the camera. You can see him walking here, maybe around the time of the crime that happened, and so on. So the agencies will actually look at the entire footage, and then they identify that yes, this appears to be the suspect, because he was seen walking, but the face is not clearly visible. But from the walking, the patterns. Okay, basically it's a cycle, repetitive cycle, right? Just having, it's actually, studies have shown, even with you know at least 2 or 3 cycles, one can be reliably, if you have good information about that, we can actually identify the person. Okay, so that's what we call gait recognition. Now what I'm trying to say is, yes, we do perform face recognition, we perform speech recognition. In fact, what you're currently performing is speech recognition. Speech recognition is all about, given speech is the input, right? For example, I'm speaking currently, right? You're making sense of it. You're trying to identify what is spoken, what is being spoken, right? Currently, it's real time. So, what is being spoken? Or if you're given with a recorded speech, for example, okay. So, if you're familiar with the language, okay, if it's spoken in English, if you're familiar with the language, you will be able to understand, recognize what was spoken. Or all that requires language familiarity for this speech recognition. So, you can perform it real time, or you can perform it with a recorded speech. Speaker, on the other hand, is different. Here we are talking about identifying, given a speech, recorded speech or real time. Okay. So instead of focusing on the content, what was spoken, we're trying to identify who spoke this. Okay. Who was the speaker? So, for example, if I give you a very old, maybe Mahatma Gandhi speech, right? Now, give a recorded speech. Now, if you're able to identify who that person is, okay, celebrities or whoever that. Now, that is a problem of speaker recognition. Now, it can be, as I said, it can be done real time. For example, we do that often without realizing, right? Let's say these days, of course, we have mobile phones. Number. If you're saved, the name appears. But let's say your friend calls you from a new number, right? Which you have not saved. So the number appears. Now, immediately you pick up, let's say you answer the call, and then this guy, if he's your friend, right, if you're familiar with his voice, so he will not require any introduction, right? So you can just say hi, and then you will realize, you will be able to recognize that person. So that's what real time in here, of course, you're doing real time speaker recognition. So similarly, yeah, I've been writing several things on this slide, and you were able to actually recognize those characters. Okay, not just recognize, you were able to recognize those individual characters, put them together, it becomes a word, and then put several words together, becomes a sentence, and then you can also recognize what that entire thing means, complete sense of it. Okay, so very high level processing that we do, human beings do, with very less effort. Okay, some many things that we don't even realize that we perform this. Now, so when I talk about pattern recognition in this field, the objective is this: can we develop computers, can we program computers, or in general machines? Okay, so because it can be robot also. Okay, so computer is a very specific term. So can we design machines, which is a more general term, that can recognize patterns? So why is it called pattern recognition? Is because, just think of it this way: we are performing recognition, but it's actually based on the underlying patterns. So as I explained to you, for example, gait. Okay, so you can see your friend walking very far away from you, but there is a certain pattern that he makes, and based on which you were able to actually identify him. So its recognition is always based on certain patterns. Similarly, for example, if I talk about face recognition, it's also there is also patterns there. For example, uh, again, how our brain processes this information is not very clear to us. Given a face image, or when you look at someone's face, what information do we really use to recognize this person? It's not very clear, because the complex processing that happens in the brain is so complex, right? We don't know completely yet. But I would say, or the general understanding is, yes, we do use some facial features, right? For example, if I ask you, so you might say, yes, we may not use explicitly, but together, sort of, holistically, right? So we use some, features of the eye, features of this eye, features of nose, mouth, and maybe a little of ear, the shape of the jaw, and all that put together. Based on that, we try to identify person. So basically, what I'm trying to say is, based on some patterns in the data. Based on some patterns in the data, we perform recognition. Therefore, it's called pattern recognition. Now, so the field of pattern recognition is all about designing machines that can perform, that can perform different recognition. So, for example, automated face recognition. We do have systems. All this we do have. It's not necessarily handwritten. It can be typewritten also, right? In fact, a lot of text characters on this slide are typewritten. So yeah, although I've just mentioned handwritten, so it can be typewritten. Okay. Now you see, we can design. We have systems now at this point that perform automated face recognition, automated speech recognition. For example, in speech to text translation, it's it's nothing but speech recognition, right? In order to create the corresponding text, given a speech, in order to create the corresponding text, the first thing is you need to recognize what is being spoken, what was spoken. Once do that, generate the corresponding text. Now, speaker recognition, yes, it's a biometrics problem. In fact, yeah, so let me also talk about that. So all these are pattern recognition problems. Okay. So if you're saying that you're developing a face recognition system, it's a pattern recognition problem. All these are pattern recognition problems. Whereas if you look at specifically, for example, if you're talking about face recognition, this becomes, because input is an image, you can also call it computer vision. This is a biometrics problem as well. Why is it a biometrics problem? Because we are interested in identifying the person. So that's a biometrics problem. It's also a computer vision problem. Why? Because input image, input is an image, we are processing it to obtain some high level information of who this person is. So we compute some attributes, and based on the attribute, we identify who the person is. So you can call it a computer vision problem. Similarly, speech recognition. So speech, of course, is not, speech is a one-dimensional signal. Okay. So it's not a computer vision, definitely. It's not a computer vision problem, but it's still a PR problem, and it is not a biometrics problem. We are not interested in identifying who the speaker is. Whereas speaker recognition, yes, this is a biometrics problem, but it's not a computer vision problem. Okay. Again, because why? There's no image involved here. Okay. So we're not, yeah, again, computer vision, if you look at this, the term computer vision comes from, very similar to pattern recognition, because we have what is called human vision system. Okay. We are gifted with human vision system. So where it's, our eyes are not just, like a camera. Although often we compare our eyes with camera, that's in fact, eyes are, sort of seamlessly connected to the brain. So when we see something, immediately information goes to the brain. Okay, they just don't capture the image, they also immediately process the information to derive some information, to make some sense of it. So exactly, that's how we look at. So human vision system is a complete package. Pair of eyes, yes, we do look at a scene, but we immediately make sense of it, right? What is it? What is this? We recognize objects, we put together everything. We can see if it's an office, or it's a beach, or it's a traffic, it's a building, and so on, right? So computer vision is all about, can we provide that? Can we design machines having such capability? So that is why it's called computer vision, human vision, computer vision. So so similarly here, we perform a lot of recognition tasks. Can we design machines that can perform recognition based on patterns? Okay. So yeah. So, but if you look at the pipeline, if you have to develop a pattern recognition system, this is a pipeline that we typically use. Okay. So of course, I'll talk about this. There have been some changes to this pipeline recently, with a lot of advancements in deep learning. How we actually look at this pipeline has slightly changed. But very similar. What I'm trying to say is the underlying pipeline remains more or less the same. You may be familiar with this, okay, because if you've worked on recognition problems, you would actually use this pipeline, okay, knowingly or unknowingly. So what it is, so for example, the first thing is a sensing device, okay, depending on the problem. So for example, if you're talking about face recognition, if you're developing a face recognition system, so the first sensing would be an appropriate camera, okay. So it could be a general purpose camera which captures 2D images, or it could be, so if you want to perform, let's say, use depth information as well, okay. Depth is something that human beings can perform, again, because of pair of eyes, two eyes we can perform. So similarly, there are some depth cameras that can estimate, for example, there are multiple techniques for that, stereo vision and so on. Even from a mono or single image, we now are able to estimate depth very accurately. Or you can have more dedicated 3D scanners, for example, laser based scanners that estimate depth very accurately. So if depth information is also something that you're able to use to recognize, but otherwise you can use general purpose camera image, those two-dimensional images. Once you have those, so it's a hardware. Now once you have an image that you capture, for example, face image, we perform what is called pre-processing. First thing is, why do we call it pre-processing? Okay, so it's also processing. Why do we call it pre-processing? The reason is, this is the most important stage. This is the core processing stage. Therefore, because this precedes that, we call it pre-processing. And this pre-processing also sometimes may not be, if not required, it may not be part of your pipeline. You can just remove this if it's not required. But this is always going to be part of pipeline. This is going to be part of pipeline. And this is also going to be part of your pipeline. Whereas pre-processing, if it's not required, we can remove it. So what is typically, what do we do here in this stage? For example, denoising. Okay, denoising can be part of it, or it can be enhancement. Okay, if you want to improve the image, you can perform enhancement. If you think the captured image has some noise, remove it. Yes, you can do that. For example, in face recognition, this can even be face detection. Okay, so when you perform face recognition, the first step is face detection. What that means is, uh, let's say you have an image which is not a sort of an image of a frontal shot. If you have an image like this, you don't require any face detection, right? This is already a face image. But if you have an image of a scene where there's a human being, and there are other things also, there's a car here, maybe there's a dog here, there's a cat here, there are multiple objects, there's some background as well. Now if you feed this directly into the face recognition algorithm, it will not perform well. The reason is, it will look at the entire thing, okay. Whereas if you detect the face first, what do you mean by detect? Detection is nothing but a localization problem, okay. We're trying to identify where the object of interest is present in the given image. Now here, given this car, dog, cat, and so on, this is the object of interest, human face. So detect it, localize it, and then you can crop. For example, once you detect, the location, sort of a bounding box is what we call in image processing. So you can take that out, and then process this fed into a face recognition algorithm to recognize who this person is. So that can be also part of pre-processing here. Now the next step is, this is the most important stage, called pattern representation. As I said, yeah, so often, in fact, at all times, output of pre-processing and input to the pre-processing, they are of the same format. Okay, if this is an image, this would be also an image. This could be, of course, this could be a better image, enhanced image, a denoised image, or image after face detection, so on. But image type, data type remains the same. If this is an image, this is also an image. If this is, for example, a speaker recognition system, this would be a microphone sort of a device, okay. And then you have a speech signal, this would also be a speech signal, maybe enhanced or noise removed and so on. But here in the pattern representation stage, what we're trying to do is, we now changing the format. Now we are changing the format so that the subsequent system that takes the final decision means, for example, if it's a face recognition, it's trying to identify who this person is. Okay, it's a person of X, whether it's a person image of Y, whether it's an image of Z, and so on. Now, so we are turning this data into a format that this decision making stage can easily use. what format it is. Remember, we this system decision making module should depend on important patterns in the data. That's a very important point. This decision making stage, what is involved here, I'll talk about that. But this decision making stage should utilize important patterns in the data, important features in the data, and that will help in accurate decision making. So that is what we call pattern representation. So we need to come up with a numerical vector, typically what we call feature vector, that has all useful information. Okay, that includes all useful information of the object in the input image. Okay, so this would be a very concise numerical feature vector, and we also call this process, sometimes we also call it, in fact this may be more popular, feature extraction. Okay, so whereas this is a more standard formal term, pattern representation. So we are representing the patterns in this form, a lot of important patterns here in this data, and that we are representing in a concise numerical form, and that this decision making stage can utilize to recognize who this person is. Okay, for example, in a simple biometric I mentioned to you, so given an image of a face, you can compute certain features like, eye feature, this feature, and so on. So put together, make it a feature vector, and then you can compare two feature vectors from two images to decide whether it is of the same person or of not of the same person, and so on. Sometimes, so I hope this is clear to you, pattern representation, which is also known as feature extraction. Sometimes we also perform what is called feature selection at this stage. Often what happens is, in the feature extraction stage, the features are, you include features based on some intuitive knowledge. Okay, so it's like this. You you know you think that this feature could be good, could be contributing to the decision making. You think this feature also could be very useful, would be useful for the final decision making, and so on. So you put together a feature vector, and that results in, let's say, a very large set of features. Now it's possible that some of the features here, maybe this feature, some of the features may not be really useful for decision making. Okay, it's also possible that some of these features, which you can actually think of as an independent variable, because based on this, your system is trying to decide, so this is an input or independent variable, so, and this is the output is a dependent variable. I'm talking about this final decision making stage. So these variables can also be highly correlated. In fact, in the face recognition system, that happens here. For example, if you think width of the left eye, if you compute both of them as two separate features, it's possible that this eye and this eye width, because of the symmetry of our face, they may be very highly correlated, these two features. Okay, if this, for example, is 5, this is also likely to be 5. On a different person, if this is 3, this is also like, which means these are highly correlated. You don't require those features both together, right? You can retain one and you can discard the other. That's exactly what feature selection does. Okay, there are various ways to do that. So basically what it does is, given a original feature set, high dimensional feature set, original feature set of dimension, let's say n, having n features, and it tries to identify a lower dimensional feature set, okay, of k, which is much less than n. So once you identify these features which are really useful for the task, and then you can go ahead with, based on that, you can perform decision making. Okay, how we do that, there are, of course, various kinds of feature selection techniques. We'll not get into that. For example, dimensional reduction, PCA, LDA, these are all dimensional reduction based, but other feature selection also you can perform, recursive feature elimination based on correlation and so on, right? There are many techniques to perform this. So underlying concept is this: given an original set of features, large number of features, high dimensional feature vector, obtain a lower dimensional feature vector. This can be a subset. In feature selection, typically this is a subset of the original feature. But if you're using dimensional reduction techniques, these are not going to be, this is not going to be a subset of the original feature set. This will undergo some linear, in this case linear, but it can be non-linear dimensional reduction as well, to obtain this lower dimensional representation. And using the lower dimensional representation, finally, this decision making stage. Now, what is typically involved here? You can use the classifiers, right? If you, again, this part is where machine learning comes into picture. Okay, often, although in biometrics we don't require, we sometimes we just perform, for example, we can directly perform computation comparison using Euclidean distance, and then based on a threshold we can decide and so on. But you can also use classifiers. Okay, so in fact, the current state of the art always uses, for example, once you have the feature, you can train a classifier, say that, these are facial features, for example, say that at the same time you provide the label, this is of X. Next set of features, say that, this is of user Y. So basically, if you're handling, let's say, 10 users in a system, so you can train this as a 10 class classification problem. Okay, face recognition, it can be seen as a, based on the facial features that we compute, feature vector, this can be seen as a 10 class classification problem. Given this feature vector input, so the model predicts whether it belongs to this class, means this user identity, or this class, and so on. Okay. Or it can be 100 class or 1000 class, depending on, the scale of the system. Now, yeah, so whatever we've discussed so far, so I just summarized here. I'll talk about this point later, the last point, very important, but we'll talk about that later. Yeah, so pattern representation is all about, it's actually the most important component of your PR system. Okay, it's a core of the PR system, and it involves feature extraction and, if required, feature selection also. And you see, all the important information in the input data, it can be a signal, image, so on, those are concisely represented in, represented in the numerical form. Okay, numerical feature vector. And once you have that feature vector, you can train a classifier to perform the decision, make the decision. You can use, the conventional support vector machine, decision tree, artificial neural network, and so on, base classifiers, to perform the final classification and predict the class. Okay, so recognition is basically a classification problem at that stage. Now, what are the desirable, when you talk about features, okay, when you're developing a pattern representation system, when you talk about features, what are the desirable properties of the features? Mainly, of course, the list is slightly long, but if you look at this two important aspects, it is discriminability and invariance. These are very important things to understand. Okay, what is discriminability? So, for example, let's say I give you a scenario. So let's say biometric system, so face recognition system. So you have an image here, or you have an image. Or let's say these are images of same person. Maybe camera has captured, there's some factor. Maybe here in this case, the camera is closer to his face. So that, that is why in the image you have the face that occupies larger region, more pixels here. Whereas here the camera is slightly far. So you have a face image of the same person, but you can, this occupies only a small region, less number of pixels here, of the same person. Let's say user number one. Now, when you compute features, okay, same features you compute from this image as well. How to compute features? That is where your image analysis come into picture. Given an image, perform some basic image processing algorithm, perform some basic image processing, edge detection, for example, followed by some other this. So you end up with what we call attributes or features or independent variable values, basically. And now you have set of features, same set of features you can capture from here. Okay, for example, eye width, width of this eye, length of the nose, width of the mouth, shape of the jaw, whatever, right? Somehow you computed those in an automated manner from the given image. Now you compute those same features from this image as well, this part of the image, okay, after detecting, for example, face. Now, when you compare them, okay, let's say for simplicity, let's use Euclidean distance, okay. So when you compare these two feature vectors, set of features, okay, do you want this score to be Euclidean distance to be very large, or do you want it to be very small?
Hello?
Yeah.
Can have break for 5 to 10 minutes.
Okay, so we can have a break then. So yeah, but think about this question. So yeah,
Yes.
shall we have a 5 minutes break?
Okay, sir.
Yeah, so we'll come back around 12:40.
Okay, okay, sir.
Okay. Okay, so are you all back?
Okay.
Yeah. Yeah. So the point was that I asked you was, so when you have this input image and this input image, face images are of the same user, right? You computed this set of features from this image as well as you've done the same with this image as well. Now, when you compare them, with, let's say with the help of Euclidean distance, okay, which is a distance measure, okay, not a similarity measure, it's a distance measure, dissimilarity measure rather. Should this be the score that you get? Do you want this to be high or do you want this to be low? Yeah, so that's the question. Yeah, some of you said large. My question is, what do you want? You want it to be as low as possible, correct? You want it to be as low as possible, a very small score. If the value of Euclidean distance is small, what does it indicate? It indicates that in the chances are that these are very similar, vectors are similar, but we are not talking about vector. We want to have some inference about the input images, which means it's likely that the two images are of the same user. You would be able to recognize basically, right? I mentioned to you images are indeed of the same user. Therefore, you want Euclidean distance to be as small as possible, okay, as close to zero as possible, so that which indicates that the feature vectors are very similar, and thus we can infer that yes, these are of the same user. Otherwise, if the score is very large, you will not be able to infer that, right? Correct, accurate recognition. Now, for that to happen, for these two feature vectors to have a very small Euclidean distance, remember, input has a lot of variability here. Okay, what is the variability here? I mentioned about scale variability, right? So you can see here image, and almost the face occupies the entire image, whereas you have this entire image, whereas his face occupies a very small region. Here this is significant variability in the input image. Despite that, to make these features similar, which means this is a point here, features should be invariant. Okay, it's a second point. Okay, so I'll come to this later. This set of features that you compute ideally should be invariant to what we call intra-class variations. So why is it intra-class? Because it belongs to the same user. As I said, if you're talking about face recognition as a classification problem, if you want to look at it from that perspective, it becomes every user becomes every class. Okay, every user becomes it should be treated as a class. Okay, user 1 is a class, user 2 is a second class, user 3 the third class, and so on. So intra-class variation means within the class you can have set of images of the same person, but looking there can be some differences. Here it's a scale. It could be illumination as well, right? For example, one image is you have taken in a very nice lit scenario, but maybe the second image you have captured in a outdoor scenario which with a sort of washed out appearance, a lot of exposure to light. Maybe the third image is in the night, very low light conditions. So this will look, so it could be illumination changes that can cause uh, the intra-class variation. Okay, but despite that, you want these features to be ideally, that's what I'm saying, I'm talking about desirable properties of the features. You want these features to be similar. Okay, which means you want them to be invariant to intra-class variations. Okay, so that's a nice property to have. And then how to have it, again, there are a lot of, in fact, if you look at the literature, for example, if I talk about face recognition, people have focused on this specific problem, how to come up with how to develop systems that are invariant to illumination. So post invariant illumination. Post means, for example, in this particular image, user is looking straight, frontal shot. In this, maybe he may be looking slightly to the left or maybe slightly to the right, or if it could be more degree of rotation of his neck and so on, right? So these are all called pose variations. He might look up, look down slightly, so on. So those are called pose variations. So researchers have actually focused on this, right? So post invariant face recognition, elimination invariant face recognition, expression invariant. Expression also causes, right? For example, this two can be of the face images of the two same person, okay, two images of the same person, but here it may be neutral expression, here maybe maybe you captured him while he's maybe laughing, okay, so which means maybe the mouth is wide open, eyes are small, whatever, right? So there can be significant variations caused by expression changes, okay, but despite that, you want the feature vectors that you compute to be highly similar, so that whatever similarity you compute should be high, or if you're computing Euclidean distance, should be as low as possible, so that you correctly recognize that person. So that's about the invariance part. For discriminability, you have very clear what you want. For example, you can think of this way: two images of two different users. So this is of user one, and this is of user two. So you have a face image, you have a face image of this user. Now, again, you compute a set of features from this image, you compute the same set of features from the second image. Now, when you compare them, let's say Euclidean distance for simplicity. Now, in this case, you want this to be as high as possible, because these two images samples, they belong to two different classes. Okay, this is of user one, this is of another user. Okay, basically, so this is an example of class one, this is an example of, let's say, class two. These are two different examples, data points belonging to two different classes. Okay, so I'm using some terminologies, machine learning terminologies like examples and data points. I believe these are familiar to you. Or in this case, yes, just an image. Okay, so you have two images belonging to two different users. Therefore, you want these features to be as dissimilar as possible. Okay, and that is what we say discriminability is. If the features are very different, we can say that the set of features that you have identified, that you computed, it has very high discriminability. It is able to discriminate between the two classes, two or more classes. Here for simplicity, I'm considering two classes, but in general you have multi class problem, multiple classes, multiple users. So if you're talking biometrics, and therefore uh, the features have a lot of discriminability property. Okay, if it's able to, if the score is high, dissimilarity is high, which means it has a lot of discriminability. I hope this is clear to you. And yeah, so something that is interesting, let me just, yeah, so we have just another 5 10 minutes or so. So yeah, so if you look at the first completely automated, so what is interesting is, I just want to, before we end, I want to present what has changed over the years, how we look at uh, how we look at this pipeline, what changes have happened, how this has evolved, for example, with advancements in, because here is where I said machine learning comes into picture. In a conventional pipeline, if you look at it, so this is a sensor, some sort of a hardware, camera, and so on. So here is where processing begins, and this is the core processing stage. These two are completely signal image processing, uh, you know, components of your pipeline. Okay, part stages of your pipeline. So if you have to perform anything here in a conventional system, yes, you do require good signal processing knowledge. For example, denoising, you might want to use some sort of filters, perform some filtering. Even in images, we use some, for example, moving average filter, simplest form of noise suppression, denoising, or you can use Gaussian filter, okay, or more advanced filters also. But you require good knowledge of signal and image processing, okay, in order to design algorithms for this. Similarly, in order to, for example, even after enhancement, if you have a face image and if you have to compute these features, you have to identify this, landmark points and distances between them. So all this will require signal and image processing, expertise. Whereas this, of course, requires, use an existing algorithm model, for example, support vector machine, train the classifier using a set of basically supervised learning. Okay, so for every feature input, you also have the correspondingly, this belongs to user one, this belongs to user one, and so on, right? Now you train this classifier, it performs. Now that's how it has been. But if you look at this, in the very beginning, yes, of course, even this did not exist. Okay, here is where we used a simple Euclidean distance to compare, for example, and then identify here. But what I want to tell you is how the thought process was at that point. Okay, So if you look at this, it's a very simple system. This was the first fully completely automated face recognition system reported in the literature. They may have been something before that, but it's not reported. Now, the first reported system was actually developed by Professor Kanade, is an emeritus professor at CMU. So, of course, in addition to this work, this was during his PhD, when he was back in Japan, and then he moved to the US. Now, uh, and he continues to be a professor, and he made further significant contribution to this computer vision as well, even after this. Now, in this contribution, what is this? So you had an image. So at that point, the cameras were available that can capture grayscale images. Okay, so what we typically refer to as black and white, although it's strictly not black and white. So it's not just black and white. So in addition to black and white, you have all other shades of gray, or different shades of gray rather. Okay, so grayscale image is what we call that. So grayscale, given a grayscale face image, so he first is done what he computed what we call edge image. Okay, edges in the image. How to compute edges? Again, you can compute edges using some basic filtering operations, spatial filtering operations, right? If you're familiar with convolution operation, you can design some, um, in order to compute edge images, you require actually some sort of a high pass filter. Okay, so design a high pass filter and then followed by some post processing. For example, canny edge detector. If you're familiar with fundamental image processing techniques, you can use canny edge robot. Um, yeah, there are David Marr also proposed some, yeah, Marr Hildreth um, edge detection algorithm and so on. So you can use those edge detection algorithm, compute edge image, and once you have the edge image, so he again developed an program, right? So image processing program, so which actually measures, identifies this points, for example, this center of the eye, center of this eye, okay, and then based on that, he computed several things. This distance, you can see here, width of this eye, and some angle measurements also. He estimated some angles, okay, so that shape of those nose can be captured, and then you can see length from this point to this point, some slightly under the ear, and then some angles here to capture the shape of the jaw. Put together, he actually, yes, in fact, he performed some sort of feature selection also, although he did not do it explicitly using existing techniques. Again, I don't think any feature selection techniques existed at that point to perform systematic feature selection. But here, what is done? Some sort of a recursive feature elimination. So he identified some subset. He tried different subset of this original set of features, and then finally proposed that he said that this is the set of 16 features very useful for face recognition. Okay, finally. Okay, so these are the set of 16 features, a mix of some distances, some angular measurements, some ratios as well, and forming the 16 dimensional feature vector. So given an image, he he developed an algorithm. Okay, so I'm using some basic image processing using edge computation, edge image, and then so on, post processing that to compute those 16 features and then perform matching. Okay, and then of course it was a very small data set at that point of 20 different subjects or users, and he achieved an accuracy of 75%. At that point, of course, something to be excited about, because this is 1970s and this is the first reported face recognition method. But now, if you look at it, over the years, we've done, we have achieved a lot of advancements in this. Okay, so if you look at it, after that, yes, there have been several methods that have. So mostly research is focused on this stage. Okay, so sensors, of course, there's nothing to do with us. This is we don't deal with sensor design. We do only after compute we capture the image or data signal. Okay, so we can of course focus on this, but this can provide offer very little improvement. Even if you focus more on this, it cannot provide significant improvement in the overall accuracy, recognition accuracy. But if you focus here, and again, this is also not something in our area of expertise because it's machine learning. Whereas signal image processing research is entirely focused on this. Can we come up with new feature extraction techniques? Given an image, can we come up with new feature extraction technique that will capture useful patterns from the data and represent in the. So if you look at early 2000s and so on, late 90s, early 2000s, all the focus has been on this. And several researchers came up with what we call generic feature descriptors. For example, you may have heard of LBP, local binary pattern, and SIFT features, and so on, right? So, which identifies some landmark points, describes them locally using some gradient information, and then performs matching. So all these generic features, okay, generic feature descriptors in computer vision, these were developed during the time, okay, so 95 to maybe 2010. So binary statistical image features, okay. So all these are mostly texture features. Texture in image means, if you look at a neighborhood, how this intensity values change in a small neighborhood, okay. So how efficiently we are able to represent that in the form of a numerical representation. That was the focus of all this, because if you're able to represent that, you can capture a lot of useful information from the image, and that can be used for recognition. But recently, maybe since 2012 or so, the the direction of research has changed significantly. And this is when the first time the CNN, although CNN, if you look at the original CNN, the LANIT was actually proposed in way back in 1989, I believe. Okay, this was the first CNN that appeared in the literature around 87, 89. Did not gain much popularity due to various reasons. One, of course, there was actually, you can't go much deep because of the vanishing gradient problem. And then you had, there was no GPUs available at that point to train such models. Okay, so it was time consuming. But in 2012, the model called LXNet, if you look at it, it's very similar to LANIT, okay, in terms of architecture. But this one, the very challenging image classification contest, you know so on an image classification context, basically, having thousands of different classes, it's a roughly 1,000 class classification problem, right? And that was the first time a, a, a convolutional neural network, a deep learning model, won the competition. And since then, we know what has happened, right? So a lot of interest in CNNs initially, and leading to developing various different architectures, ResNet, VGG, and so on. And then, of course, now transformers, vision transformers, and even diffusion models. So there has been a lot of advancements, and the advantage with CNN, for example, is, but if you look at the underlying principle, CNN also does the same, right? It relies on the on a set of features to compute image features. So given an image, for example, we know that if you operate a filter on this, let's say low pass filter on this, you get an image response, which is a response of this filtering operation, where the features are suppressed, becomes blurry. Similarly, if you have a same image, and now if you operate a high pass filter on this, okay, different filter on this, you get a different response. That's a basic idea used in CNN. So what they've done is they have used multiple images, of course in multiple stages also, multiple filters, and these filters are not designed. Typically, we design the filter. When I say design the filter, we design the coefficients of the filter, okay, for a specific purpose. If you want to blur, you can have a low pass filter here, okay, perform that low pass filtering on this image, you get a blurred image. If you want to enhance, you design a high pass filter, operate on this image, you get a enhanced image. But here what I've done, taken a set of filters, they were not designed by hand, but instead this was actually posed as a formulated as a learning problem. So the filter values, coefficients, were actually learned for that specific task, okay. So that is where the learning comes into picture. And so the filters itself are sort of adaptive for the problem, learn the filters, and then they operate on the image, input image, to capture those features, and based on the features we perform classification. So the advantage with that is, you can now, so these two stages have now are merged. Okay, in the pattern recognition pipeline, now we have, if you're using CNN, for example, the advantage is it can learn features. We don't have to have a lot of knowledge about how to handle images, how to perform, let's say, discrete wavelet transform to capture those features, or LBP to capture LBP features, or SIFT to capture SIFT features. We don't require all that knowledge. We can have an CNN set of having a set of filters in multiple stages, okay. That is what we call hierarchical learning. And those filter weights, those filters will be designed during the training stage. And then once those filters are designed, so you can operate those filters on the input image directly. The learned filters will operate directly on the input image to capture a set of features, and then classification will also. So it's an integrated architecture. It performs feature extraction, rather feature learning. We should not say feature extraction, because feature extraction is more where there is a user, sorry, the designer does this. Here, designer only designs the architecture, and then during the learning stage, it does representation learning, okay, feature learning or representation learning. It learns the features and then performs classification. So I'll stop at this point. Let me know if you have any questions. So yeah, so we had a lot of things to, I had planned a lot of things, but then anyway, I summarized what I wanted to discuss. So yeah. Yeah, let me know if you have any questions or anything. Otherwise, we'll end this session. Yeah, go ahead, Shamli. Uh, about recording, please check with Dr. Hemant Meena.
Yes, Shamli, recording will be available on Canvas. Uh, I will inform you in group. Aditya. Okay, sir. Thank you. Sir, Hemant
Okay,
sir is not present in the meeting, sir. I will inform him.
that's fine. Whoever is coordinating from your side. Yeah, Shamli wanted to. Okay, maybe it was by mistake.
Sir,
Pattern
one
classification and
question,
pattern
sir.
recognition. Yes,
Sir,
correct. Yeah,
sir, it's pattern
Sneha has a
classification.
question. Let me just. Okay, I'm not sure how. Let me try if I'll unmute. Let me first answer Snehal's question. And in the meantime, is it possible for you to unmute Shamli?
Sir, there is no provision to unmute for participants, sir, in this FTP.
Okay, so Shamli, the only way is then you can type in the chat box. So,
Shamli, you can type.
yeah. So Snehal, yes, that's correct. In fact, the reason why I mentioned that as well. Oh, okay. I may not have indicated at that point. This is less popular term. It's actually the same pattern recognition and pattern. In fact, the book, right, the classic book on pattern recognition is by, if you're interested, Duda, Hart, and Stock. Okay, so these three researchers, authors have actually written a book on pattern recognition, which is actually, they call it pattern classification. The reason why, again, see, as I mentioned, recognition, if you look at it from the machine learning perspective, finally, what are we trying to do? So, given image, face recognition, right? We are trying to sort of classify. At the end, it's a classification problem. So it's also called classification. But this is more popular term, widely used as compared to a pattern classification. It's the same. Yeah, typically that's correct. Guidelines, of course, are available, but it's very hard to predict which approach would give you the best performance. Very hard. But typically, we would still go with this pipeline. We do use this pipeline only when we have limited amount of data. When you have limited amount of data, computing the features, we call it, what we call, sort of handcrafted features or human crafted features, and then using some machine learning techniques to classify. This is done when you have limited amount of data. But when you have large amount of data, because typically these architectures, for example, CNN, having multiple layers, right, several parameters, so therefore you require more data for this models to successfully learn the features. Okay, so when you have large data, go for this sort of an integrated approach which learns features and then performs classification. And otherwise, go with when you have very limited data, you can go with the conventional approach. But it's very hard, right at the beginning. It's very hard to tell you that this, for a given problem, this is the best approach. You will have to try with both approaches. And in fact, even in deep learning, you have different models. Try with different model. We call it, in general, we call it model selection. Okay, model selection. You will have to perform model selection, identify the best model. So do we have to use feature extraction, feature selection when we use no, no. we don't have to use, we don't have to do it explicitly, correct? Shamli's question is, do we have to perform feature extraction and feature selection when we use CNN? We don't do it explicitly, but remember, feature extraction is not the right word when it comes to CNN, but it also does it. Instead, what it does is it does feature learning. Okay, it also compute features. See, CNN is not a complete black box. You can actually see inside what is happening every layer. So what happens is initial layers, it does what is called feature learning. At the end of it, if you tap the output, that would be like a feature vector. Okay, if you tap the output, but then if you go on, you have what is called a classification head, typically your fully connected layers that perform classification. So it's a sort of an integrated approach. It does initial layers, does feature learning, learns the feature from the input data, which can be compared with your feature extraction. If a designer does it, we call it feature extraction. If the CNN does it, we call it feature learning. And but the output is equivalent. Okay, output of the feature learning stage, if you tap into that, take it out, that will look like very similar to our feature, our feature vector. And then you can perform classification in the conventional way, or you can use the classification head of the CNN to perform classification. So you don't have to perform explicitly, but that is done inside CNN by its own. Okay. Okay, so there are some other questions also. So, it's necessary to work on grayscale images on various image texture. What are the implications of working color? No, that depends. Again, that depends on the problem, Parvesh. So, in some case, Pravesh, yeah, in some cases, color information can be very crucial for uh, recognition. Okay, so again, that depends on your intuition, right? Your understanding of the problem. If you think that color information is useful, you can work with color images. Okay, and if you think if it is just texture, for example, we can go with grayscale images. Okay, if you're going to rely entirely on texture, you can use grayscale images and then perform it. Okay, but if you think color image, using the color information can help us improve the performance, yes, you can go with, for example, if you're talking about fingerprint, I've not seen, maybe there has been some initial study, but I don't remember any paper that uses color fingerprint images. Of course, there are scanners that capture, the capturing technique itself is different, but we have now optical capturing as well. So we can capture color images if required. But even if you capture color images, we turn that into grayscale because there is no useful color information uh, in the fingerprint. Okay, of course, skin color varies, but what I'm trying to say is it's not going to be a very important factor when it comes to recognition. More important are other patterns, other features in the fingerprint that we should focus on. So color is not so important. So such applications, forget about color. Even if it's a color image that you capture, you can turn this into grayscale and then so it depends on the problem. But in some cases, color information can be very useful, and in that case, yes, you can use the RGB image. That depends on the problem. Oh, okay. So Vivek asked, how did we handle? Yeah, again, how did we handle? Again, we actually trained the model on, when we trained the technique, right? When trained the model, we trained the model on different images of the person. That's one way of doing it. Augmentation. Have you heard of augmentation? For example, we may have captured only three images of a person. Then what we do, we can augment our data set. We can actually perform, we can add some noise, we can rotate it, we can do several things, obtain, maybe from three we can obtain 10 different images by making some altering, basically image manipulation. Once you get this set of images, we can train our model, we can basically make our model see these images of the person instead of just three images that we capture. Okay, so that model knows, yes, model has seen this image, model has seen when the user has turned this and so on. So this is what we call typically augmentation. So this one way of handling these issues of front, not frontal. See, frontal post based image recognition is a very trivial task. Okay, anybody can do these days. Even you can achieve close to 100, very close to 100 accuracy. But the challenge is when you have significant changes in the input, as I said, post variations, lighting, and so on. Does pattern recognition only for images or image processing? Or is it for pattern recognition? Does pattern recognition only for images, image processing is it for pattern recognition? I did not get that question, Shubha, correctly. So if you're talking about pattern recognition, does it always involve image processing? The answer is no. I think I mentioned that elsewhere. See, for example, this involves image processing, or more specifically computer vision, high level, whereas this has nothing to do with images. This is simply one-dimensional signals. Here, it's also one-dimensional signal processing. Here, you will be taking an image. When you're developing a designing system, you will take a capture an image and then recognize character, put together to form words, and then words will be put together to form sentence and make meaningful inference. So yes, in this case also it's an image or computer vision system, whereas here it's a signal processing. This is also going to be signal processing. So I'm not sure exactly what your question is. So yeah, any other questions? Okay, great. So Lakshmi Narasimhan asks, how does pattern recognition system balance discrimination scale in when the same person appears at different distances? Okay. Uh, See, uh, the question of scale, let's say, so same person appear different. So when the same person appears at different scales, so yeah, that's what I said. So you want your the features that you compute to be somehow invariant to the scale variation. That's exactly what is happening here. Discrimination is the other one, right? Yes, of course, I know what you're trying to see. Here, it's easy for the system. If the system is not, the features are not invariant, that might discriminate, right? Although they belong to these images belong to the same user, let's say user one. Okay, so you want these features to be how it does. Remember how it does. It's actually based on this stage. Okay, why is it stage? Because for example, this is always going to be some sort of supervised learning. Okay, so in pattern recognition or pattern classification, we would be performing supervised learning. So we provide, for example, image of a person. We capture a set of images from this. We provide it to this model, this stage. Along with that, we say yes, this is the image or a set of features that we computed from the image of user one. Similarly, even if the image there are significant changes in the image, if this also belongs to user one, again we compute those features and tell the model that yes, this also belongs to user one. And whereas when an image is of user two, you compute the set of features and then tell the model that, so during that, the model, you know how machine learning works, right? So the weights are learned. So I did not explain this in detail because this was not our focus. But then uh, you know basically what it does is it would be able to um, you have what is called a feature space. It would be able to, for example, they would be, maybe I can just show you this. Okay, so I think there's one interesting image if I can show you. Yes, you see what is happening here is, yeah, I think this will be able to, with the help of this example image, I'll be able to explain this. What I'm trying to see is, what are these dots here, green dots? All these green dot means, remember there's something called visualization also. Again, something that we cannot discuss everything in one session. What is visualization? Typically, given an image, you would be computing several features. Let's say in the original first work, we had 16 such features, facial features. Now you cannot directly visualize 16 features because it's a high dimension. So anything beyond 3, we can't plot a 3 dimension. We can plot 3 dimensional scatter plot. 2 dimensional 3 dimensional scatter plot is possible, but beyond 3 dimension we cannot plot. So what we do is, once you have this 16, let's say 16 dimensional feature vector, we reduce it to either 3 or 2, and then plot a scatter plot. So that's exactly what we've done. From each image, we've computed some set of features, facial features, and then reduce it to 3 dimension, plotted. Now this means this is all, each represents an image of this person. Why is it not at the same point? Because of intra-class variability. Because of intra-class variability, you can see these dots, there is some dispersion, but it's still a compact cluster. Similarly, what these dots mean, remember dot is a 3 dimensional point, okay, which is obtained from originally, let's say, 16 dimensional feature vector. We reduced it, we perform dimensional reduction, and then we get a 3 dimensional, and that becomes a point here. So what are these multiple points? Multiple points are actually corresponding to multiple images of the same person. Similarly, we want, see, there will be always, ideally we want multiple images of the same person to map to the same location in the feature space. That is never going to happen. There would be always some dispersion, okay, some, but we want this cluster to be as compact as possible, okay. These points, because they all belong to the same image of this person with like different conditions, these expressions, pose, as you mentioned, so on, but we still want them to be as compact as possible. At the same time, there should be a large gap between these clusters, and that's what you're talking about. Balance between this gap is what we call discrimination. The larger it is, better it is, okay. And whereas this should be as compact as possible, okay. So the features should be learned in the modern way. The features are learned in such a manner that this remains, for example, you may have heard of this, right? So what is called yeah uh, you basically, you have, that anchor point. I'm not just remembering the name. So you have a anchor point and you have a positive sample triplet. Okay, basically you form a triplet, and then you train the model in such a manner that if the two samples are two different classes, make sure that they are as far away from each other. But if the two samples are from the same class, we make sure that they're close by. So basically, yeah, so you can have this is how it is done. So in the medical field, what kind of images? Again, there is no such answer. See, MRI, if you read MRI, MRI is very useful for, uh, you know, capturing internal structures. Okay, very expensive. In fact, CT is a less expensive alternative. Okay, CT, yes, CT. If you're referring to that, CT as an X-ray, yes, because in CT you have nothing but X-ray slices. Okay, so CT and MRI, but I'm not really an expert. So, but typically what doctors do is, most cases both can be used to capture the internal structures. But then in MRI you have what is called functional MRI. Also, you can actually see, not just visualize, you can also see the how this the organs function. So this provides more information as compared to CT. But MRI is, of course, more expensive option as compared to CT. Yeah. So if you're working with JPEG images, what should be the ideal? No, again, resolution depends on the problem. That's what I said. For example, um, fingerprint, there are some standards. For the reason that fingerprints are often used by law enforcement agencies, so they have made some standards. But if you're talking about face recognition, there is no such standard. So people have even looked at very low quality, face recognition, very low resolution face recognition. Why? For example, in a forensic scenario, input can be from a surveillance camera. If the surveillance camera is here and the person is standing here, maybe he is looking at the camera but very far. Now what happens is, you have captured an image like this, a frame of the video, but the person appears here. This would be a very small image, very low resolution. Now given a database of good quality image, and so matching low to high quality images is also a research problem. So there's no such standard for face recognition, but yes, fingerprint has a standard. The reason is, it is often used by law enforcement agencies, and standard resolution is typically considered 500 pixels per inch. Okay, which means from this standard resolution fingerprint, you would be able to capture all the useful information from the fingerprint to match, to perform the matching. But if you go for higher, of course, at the higher cost, sensor cost will increase. but then you would be able to get much better features, slightly improved features, much finer features, and that will increase the recognition accuracy slightly, but it's not very high improvement. And that is why systems, most currently existing systems, also use standard resolution images, 500 dpi images. But when it comes to other biometrics, there are some standards. For example, palm, if you're talking about palm also, palm print. Okay, palm print also is a very, although I don't think any commercial systems exist, but in research a lot of people have looked at this. It's a very effective for biometric recognition. Typically here, even 150 pixels per inch suffices. Okay, even with 150 very low resolution images, we can perform accurate biometric recognition. So there's no one standard for all biometrics. It will vary. Okay, so I think if there are no questions, shall we end the session then?
Okay, sir.
Yeah,
Thank you, sir.
yeah. Thank you, and bye. Bye bye.